Hello, everyone. Welcome back to another week. I hope you're all staying safe and well. So we're just going to continue where we left off on chapter 3. We were doing some exercises. So hopefully you guys had some practice with this. We're going to just do a little bit more because this chapter has a lot of active exercises, and it'll get you used to setting up these problems and tackling word problems in general when you encounter these in all your chemistry classes. So let's go over the next exercise. So it'll be another one, so another active exercise. So for example, what distance expressed in miles will an automobile travel in 3 hours at, oops, speed of 62 miles per hour. Okay, so let's list what we have. So we have time. So we're given 3 hours. That's our time units, right? And what we want is distance, in this case. So distance, length, units, and we want miles. So we have our conversion equivalency already. So we have 62 hours. Sorry, not hours. That'll be really long. 62 miles per 1 hour. So what we want is miles, right? So what's going to go on top of the fraction is 62 miles, because once we multiply this by the hours will cancel, and what we're left with is miles. So as we do that, we have, let's set up our equation here. 3 hours times 62 miles per 1 hour. And now we see that once our hours will cancel because it's multiplication division, and then we end up with 186 miles. Okay, so work through that problem. If there are any questions whatsoever, always feel free to email me about the lectures, and I'll be happy to go over that. So let's check that. So the car, we're expecting to travel a greater number of miles than the number of hours it's traveling, right? Because if you think about it, if you're traveling less miles per hour, that means you're going really slow. So in a car, on a freeway, you should be traveling fast. So this answer would make sense that in 1 hour or in 3 hours, we will be traveling a total distance of 186 miles. Okay, I forgot to stop the time, but I think that was like maybe 2 to 3 minutes. So I'll just say 5 minutes has passed. Okay, so let's go to the next example. Okay. All right, so we're doing a lot of these so you guys get the hang of these types of problems, and it becomes like repetition. So you'll know what to do every time you see these kinds of problems for any unit conversion. Okay, so another active exercise. Let's make this red. So say a little girl broke her piggy bank and inside, and these touch controls are very sensitive. So inside, she found, well, there's a comma there. She found 2,608 pennies. How many dollars does she have? Okay, so we're given, so you can always write what you're given, and that helps you organize the information. So given is 2,608 pennies. And this is a US monetary unit or US money units. And what we want is also another US money unit. Dollars. So we for those of you who everyone probably has lived in the United States unless you're a foreign student, but 100 pennies is equal to $1. That's our monetary system. So what we can, since we want dollars, right, we can set up this way. Since we want dollars, so we want to divide both sides by 100 pennies because we want dollars. And this will be our equivalency factor right here. So that will be our factor that we're going to use. $1 for 100 over 100 pennies. So we just use dimensional analysis to set this up. 6 pennies times $1 gives us 100 pennies. So we simply move the imaginary decimal point back 2 places because it's divided by 100, right? So what we get is $26.08. So you save up pennies. I advise you to go transfer them into dollars because you get some extra cash. Okay. So we started with the larger value, right? Pennies. So since our conversion factor is a fraction and we're going to divide by 100, our value at the end should be considerably smaller. And we can check that $26 in terms of quantity of a unit, that is much smaller than 2,608. So this answer makes sense. Okay, let's move forward here. Okay, so now let's stop doing some exercises for a bit, and we're going to talk about the metric system. Oops, I think I started way below on the canvas, so now I'm almost at the end. Sorry, guys. We'll have to move to a blank one in a bit. But anyway, the metric system. So let's talk about the metric system. Actually, let's just move up. All right. So let's talk about the metric system. So as you were probably growing up in school, you probably heard about the metric system, our system of counting like measurements in increments of 10, like centimeter, decimeter, millimeter, nanometer, micrometer, etc. So the metric system is our method of measurement used by most oops. So it's used by most of the world based on a small number of basic units. And standard set of prefixes. So some things, the method of measurement is used by most of the world. So like every paper, if like scientific literature, you always see the metric system being used for measuring out quantities. And it's very simple to use because you just have to remember some prefixes and a small some units like centimeter, so units of measurement, and then the prefixes that denotes a certain power of 10 for measurement. So we'll go into the basic ones, and some of the more standard prefixes you should know. So this method is preferred by scientists for a number of reasons. So it's preferred by scientists because A, it's internationally standardized. Agreed. Whoops. It's agreed worldwide on definitions of metric units. And decimal based. So easy to manipulate and convert to other units. So it's standardized internationally, so everyone agrees, and it's based on a standard that everyone kind of uses. And when they came up with this system internationally, they all agreed that it was the system that we should use to communicate more effectively, research results and through papers and publications. So we also have this comes the next thing that comes as a result of this is called SI units. So you might have heard of the SI units. So they are subset of units. Whoa, whoops. the international system So what these units do, they describe basic, well, not basic, sorry, base units that serve as fundamental definitions. Okay, so next we'll go into what are the metric units. But first, I need to see. Oh, very interesting. Okay. Now, for some reason, it doesn't scroll down a lot for today. I don't know why. Anyway, so metric units. Let's talk about metric units. So metric units. Let's just change the pen a little bit. So metric units. So these units are identified by prefixes. So we have something called a basic unit. So units that are larger than the basic unit are larger by multiples of 10. So for example, the kilo, so the kilo unit, so it's 1,000 times larger than the basic unit. So the basic unit can be anything, meters, for length, for volume, liters, for like time, just seconds. But I don't think anyone ever says kiloseconds. They say milliseconds or microseconds, but I never heard anyone say kiloseconds. But anyway, that's another one for time. And there's other ones, but usually time, volume, and length are the most common ones. Right. So that is kilo. And then on the opposite, on the other hand, on the other side of it, we have units that are smaller than the basic unit, are smaller by multiples of 10. Well, another one is mass, right? So grams, kilograms, micrograms, nanograms. But nanograms is like virtually nothing. So nanograms is very hard to measure out. And you really need, I think, specific instruments to do that. In the lab, we work on milligram scale. Well, not milligram scale, but gram and sometimes milligram scale. But milligram is also pretty small. microgram is kind of on the fringe of what you can detect using a typical balance. But for units smaller than, say, grams, we use multiples of 10 that are smaller than the unit. So 10 to the negative 1, 10 to the negative 2, 10 to the negative third. So it refers back to scientific notation where we talked about how to represent very big and very small numbers. So this example, we can say the milliunit is 1/1000 or 10 to the negative 3 times smaller. Smaller than the basic unit. Okay, guys. So the metric system revolves around scientific notation and those multiples of 10. Okay, so those are metric units. Now let's talk about some of the metric prefixes, like so. Okay. So let's divide into large units and small units. So these are the only ones I expect you to know and memorize when you need to use them. But I haven't decided if I'm going to provide you these conversions on like quizzes and stuff. I haven't decided yet. So let's talk about the prefix, then their symbol, so the metric symbol, and what the multiple, so how you will convert to each. So prefix, tera, so you may hear like terabyte. Symbol's T, and the multiple is 10 to the 12th. So that's very large. Giga, like gigahertz or gigabyte for like, on hard drives, like you download, if you movies, if you ever bought movies online, there's several gigabytes. So lots and lots of data and lots of space required. So G, and that is 10 to the 9th. So notice that we always tend to move in like we don't go between giga and like tera because they're like they're always separated by like 100,000ths of like unit size. So we tend to not name anything in between. Just because I think we just run out of names of what to call them, basically. Okay, mega is million. So the mega is M, and that is 10 to the 6th. And I'll write out what 10 to the 6th is. It's 1 million. Just for a reference point, 1 million. Then now we go to kilo, which is 1,000. So kilo is K. Oh, we do not use capital K because capital K is already the unit for Kelvin. So we do not use that one. So we use K, lowercase k, and that is 1,000 or 10 to the third right here. Next we have hecto. Hecto is 10. No, sorry, not 10, 100. So it's H and 100 or 10 to the second. Next we have deca. Deca is 10. So like I only did a really like mnemonic for memorizing deca. Just think of it like deca. Yeah, I'm not sure if there's a unique way of thinking 10 for deca, but whenever you see like deci or deca, think of it like the tenths place or like the 10 or tenth. So deca is 10 times a meter and deci is 1/10 of a meter. So deca is DA. We don't call it lowercase d because that's already the unit for that's already the symbol for density. So deca is 10 or the base unit 10 to the first power. Okay. Now our basic unit is right here. So our unit, so this will be our unit. So this is our reference value. For example, gram, meter, and liter. So meter is for length, gram is for mass, and liter is for volume. So whenever you're referencing these prefixes, your basic unit, you'll attach these at the end for the suffix. For example, decameter, hectoliter. No one says hectoliter though. Kiloliters, rarely. That because we don't in chemistry we usually don't work with that types of volumes or types of units in general because it's huge. And unless you work in industry, you won't be working on industrial scale. But in computing, you know, this the top three largest metric units are pretty much used. For example, kilobyte, megabyte, or just I don't even say decabytes, but we say kilobytes, megabytes, you know, gigabytes. I don't know about terabytes, but well, my hard drive is actually 1 TB because I do a lot of calculations for quantum mechanics. So actually, I need all the space I can get to store those files. So, but anyway, let's talk about the bottom half now. So the small units will be over here. All right, let's just scroll down. I'm not using this canvas very effectively today. Small units. So these are the units we like to use in chemistry because they represent something on the atomic scale. But usually the only ones we've worked with are probably milli or micro. And maybe sometimes nano, but that's very rare. Okay, so let's again write out our metric unit. Our metric symbol. And our multiple. So now our multiples are going to go to the negative number because it's going to be less than the basic unit. Okay, so metric unit. So here again, we have our unit, gram, meter, liter. Hey, that rhymes. Okay. And our multiple is 1. Oh, did I not write the multiple here? Let's go back. So our multiple here is 1, 2, or 10 to the 0 power. So we know that 10 to the 0 power is 1, right? So any number to the 0 power is 1. I actually don't remember why that is, but this isn't math, so we don't need to worry about that. But remember, anything to the 0 power is 1. All right, so let's go back to our multiple here. Again, it's 10 to the 0. That's 1. Deci. So deci is just the opposite of deca. So the reason why we don't use it here is because the metric system for deci is already D. So its value is 0.1 or equals 10 to the negative 1 power. Centi, so like centimeters, so that's C. So that's 10 to the negative 2 power, or 0.01 as a decimal. Okay, so that's centi. Let's go to milli. Milli, just think of like millennium or 1,000 years. So a milli would be 1,000, or 0.001 equals 10 to the third power. Negative 3 power. Sorry, negative 3 power. Okay, micro. So micro, you may have heard like micrometers, or like micro liters or micrometers. So those are common units used. So it's used by the Greek letter mu, like this. So it's just like it's like an inverted or upside down H. That's how you write it. So that is 1/1,000,000th. So 1/1,000,000 as a fraction. So it's 0.00, 5 zeros and a 1. 0.0001, or 10 to the negative 6. So that's a very small unit. Nano is 1/1000th. So 1 over, or 10 to the negative 9. Let's say this 10 to the negative 9, but it will be 8 zeros and a 1. So that's very, very small. And then Pico. Pico is the last one we'll talk about. Pico is the opposite of 1 trillion, which is the unit P, and that is 10 to the negative 12. So these are the units you'll be kind of required to know. And if you just remember their places on or their common, just how like their multiples. If you memorize the multiples, it'll be easy to implement. And this system is easy to I wouldn't say easy, but it's much more I say reasonable to understand, because there's a very unique system of these multiples to kind of relate each one of them back. So I would the homework will go over this a lot, I think a lot. So you'll have practice using these metric units, but these are the only ones you'll have to kind of memorize. The other ones, the other unit conversions, I will provide probably as part of the quiz for you, so you don't have to memorize those. Or you're able to use kind of a formula, like a conversion sheet or formula sheet on the quizzes and exams, so you don't have to worry about memorizing those, because I know that'll be a lot. Okay, let's talk about mass and weight now, in terms of, chemistry, not in terms of chemistry, not outside of chemistry. Mass and weight. Okay, so mass and weight. So mass and weight are actually two different things. So mass is the quantity of matter. So it's the measure of the quantity so your mass will always be the same. Like if you were able to visit every planet, right? Like the moon, for example, your mass will stay the same. It won't change. However, you will feel lighter because you're not under the Earth's gravitational force anymore, which is stronger than the moon. The moon is about 1/4 of that. So like if you weigh like 200 pounds, you would feel like 50 pounds on the moon, which is incredible to think about. So so say I was 200 pounds, it feels pretty like hard to move sometimes, but on Earth, but on the moon, you'll feel very light, like you weigh 50 pounds. So the weight is a combination of the gravitational, it's a force really of your mass times the acceleration of gravity, which is like 9.8 meters per second squared. Okay, so mass is a measure of the quantity of matter, and your weight is the measure of the force of gravitational attraction on a body. So you may remember these terms from physics. If you ever took physics in high school, or maybe for those of you who are have been in college for a number of years. So the weight is proportional to mass, ratio between depends on where in the universe one happens to be. So that was relating back to the Earth and Moon example. Like how you see those people move so they can actually look like they're floating in the air while they're walking, right? So it's like you're in a bouncy house, sort of, but like in slow motion, because the gravity on the moon is so different from that on Earth. Okay. So how does this relate to chemistry? Well, we have things that refer to the mass of an object. So we can record the mass of an object using balances. So nowadays we have electronic balances, so you can it's very accurate in grams, milligram scale. So we can measure accurately the mass of an object based on using an electronic scale. Okay, and so let's talk about the SI units for mass. So hold on. Let's clear the canvas. I wanted to save it, but I think it's okay. You could just go back to the video to review it. And I don't know why it's running out so much space so quickly. Okay. So let's talk about the SI units. SI units for mass, length, and volume. So the SI unit for mass is the kilogram. So like in the US, that is not the unit we use for standard measurement. If you go to grocery stores, we don't see kilograms, we see pounds. So we'll talk about that in a few slides, I think. But for mass, it's kilogram. So I don't know if you ever like look at like in Asian countries, they always report their masses or their weights in kilograms. Like, oh, you're this certain amount of kilograms. So it's kind of weird for if you're like me, you live in America, that they don't use pounds. So I do not know why they don't, but I guess it's an American thing, right? So here's the formal definition of kilogram. You do not need to know the formal definition. Just know it's the basic, it's the SI unit for like mass. So it's unit of mass equal to the mass of the international prototype kilogram. Okay, I jumped too ahead of myself. What I meant to say, maybe, kilogram is like what you usually it's a standard unit for like reporting maybe like body weight, but it comes from usually when we see large quantities of mass, we usually use kilogram. That's the most common unit for it. You don't ever see um like megagram. Those are huge numbers. So kilograms the most common. That's what I wanted to say. So the basic unit is grams. So like in most chemistry problems, you'll always see either kilograms or grams is more common for talking about like stoichiometric problems. But we'll get into that much later though. So meter. So these are just formal definitions for these units. Length of the path by light in a vacuum in 1/299,092,458 seconds. So do not worry about that definition. That is just a definition of a meter. So we need reference to be able to know how long something is, right? Because we just say meter, we don't know what that means, right? So we need a formal definition. Same with kilogram. So there's always these formal definitions or a starting point to kind of gauge a more so we can actually use them as a reference point for other metric units. So you can adequately describe a unit of measurement based on that reference. So if we didn't have these references, we wouldn't know what a picometer is or a centimeter, because it'll be a reference from a meter, which we do not know. So we always need those formal definitions or that base measurement to kind of base other ones on. Okay. So meter is the base unit. Longer is called, so longer length unit is kilometer. So it's kilometer or kilometer. I don't really have a preference for how you say it, but it doesn't matter. So kilometer, kilometer is a longer length unit. Usually kilometer, you can equate that to miles here in the U.S. They're frequent units we use for driving and traveling. Centimeter. So you may hear a centimeter on on rulers, and centimeters usually used also to report one's height. In Asian countries, here we use a combination. Well, we don't use a combination. We use we don't use centimeters. We use a combination of feet and inches. So centimeter, cm, and millimeter, or mm, two common units on one side on the rulers, is used for small distances. Okay, guys. Okay, everyone. Let's move on. Okay, let me just check the time really quick. All right, about 30 minutes left. So let's talk about the unit for volume. SI unit for your volume. SI unit for volume is the cubic meter. So that is the cubic meter. You may be wondering why isn't it milliliter? Well, we'll get into that in a minute. So what is the cubic meter? Well, it's related to the cubic centimeter. So volume is actually a 3D it's a 3D quantity. So length is one dimension, like one dimension this way. Area is two dimensions. You have a length and a width. That gives you an area. But for volume, it's like looking into like a box. It has length, width, length, and then in a third dimension is height. So you can actually, you can fill up the box and it'll be a 3D object. So that's what volume has to be, because when you have containers, liquids, they will fill up to the size in their container or the maximum volume the container can hold. So volume is a three-dimensional unit. So cubic centimeter is a common one. Centimeters cubed to depict volume. So unit of volume equal to the volume of a cube with a 1 centimeter width, length, and height. So liter and milliliter so these are basic units for expressing volume of liquids and gases. Okay, Okay. So you may guys recall that one meter cubed is equal to 1 liter, and 1 centimeter cubed is also 1 milliliter. So let me just double check that value. Okay. So one thing you want to remember, so I was actually mistaken, so ignore me. So I'll just put the values here. So don't worry about 1 meter cubed. We for volume we don't usually use that. The one you want to keep in mind is this: 1 centimeter cubed equals 1 milliliter. And the reason that is because you have a the reason we say that is because we have a cube like so. And each side is and each side is one centimeter in length and distance. We say that that will have the same volume if you fill that cube up with a liquid. Well, the volume will be equal and to 1 milliliter. So that's why we say that's how we get this equation right here. All right, so that's the most common one that you should know. The other ones, you can do it by dimensional analysis. For example, let's say we have another cube. So here's another cube. Now say the dimensions were so say the side right here is 1 liter, or 1 right, 1 meter. Or not 1 liter, sorry. It's 1 meter. So 1 meter cubed. Oh, okay. So so it was 1 meter cubed, right? So the difference between 1 meter and 1 centimeter is 100 there's 10, it's a difference of 10 meters, right? So if you have 1 meter, you'll have 10 centimeters, and then 10 times 10 times 10 is 1,000 will be equated to 1,000 milliliters. So yeah, it should be 1 liter, right? Because but anyway, I'm getting conflicting answers when I Google it, so I wouldn't worry about that one too much. But I still stand by that. I think that I mean 1 meter squared equals 1 liter. We can also look at it this way. So so say like this: 1 meter squared or cubed times 1 meter is 1 meter is 100 centimeters, right? Times 1 meter, 100 centimeters times 1 meter, 100 centimeters. So the reason we have to cancel, the reason why I had to write this out 3 times is because to cancel out a meter cubed, you need to cancel out three conversion factors of it to get the cube ratio. So we cancel out meters right here. So that will give us 1 million. So 10 to the 6th centimeters cubed. Oh, I see now. Okay. And then 1 millionth centimeters cubed. So that will be 10 million milliliters, right? As we, oops, sorry. Equals, I see now. Okay. So the easiest way to do it, guys, is to just convert it to centimeters cubed and then figure out from there the liters. So that is about, and we divide that by 1,000, right? Times 10 to the 3rd milliliters per liter. And what we get is 1,000 liters. And that makes sense, right? Because you have a meter in height of volume. So say you have a box or a container, say that's 1 meter in length, right? In height. That's going to be pretty high. And I don't think you can fit like 1 liter, like maybe of water in there. So always try to rationalize these units by thinking in terms like, oh, will a 1 liter bottle fill this high of a box? Stuff like that. Try to relate it back to stuff you see in real life, and it can make visualizing these things a little bit easier. So sorry about that little tangent, but I'm glad I went over it and did not leave you guys like with a half-hearted answer. So sorry for taking that long about method, but I'm glad we were able to prove it mathematically. So this is actually incorrect. So let's correct this. This is 1,000 liters. All right. So the actual equivalency we want to say is 1 decameter. No, not decameter. Decimeter cubed is 1 liter. So that one is the one we want. And we could probably prove this again by dimensional analysis. So as practice, if you want, you can go through this dimensional analysis setup we want here and kind of prove that the decimeter cubed is equal to 1 liter. So sorry about that tangent, guys. All right, let's move on. So since we talked about kilograms, let's talk about the international prototype kilogram. So how they decide upon is it has some historical reference. So there's a slide called Figure 3.7. It has a picture of what I'm about to describe to you. So the international prototype kilogram. So remember, for base units, we need a reference to base that all those metric units on. So the SI unit for mass is the kilogram. So we always reference things to the kilogram, but the basic unit is grams because that's where we use all the prefixes for multiples of 10 based upon. So what is the kilogram defined as? Well, it is the mass of a platinum – iridium cylinder stored in a vault in France. So that is our basic for the kilogram. So that's the mass of this cylinder stored in a vault. So it's this chemical equipment that's stored, archived in the vault. And a useful unit that we, for people in America, so 1 kilogram equals 2.2 pounds. So take your weight divided by 2. That's how much you weigh in kilograms. So that is our conversion here. So for example, if you see this conversion and you need it on a quiz or exam, I'll probably give it to you because this is not metric unit. This is it's the U.S. unit that comes from the metric unit, but it's not part of the metric system. So don't worry about these type of conversions. We will, or I will at least provide them for you. Okay. Now we're going to talk about measurements that are often seen that are not part of the metric system. All right. So let's talk about length measurements. So 1 inch is defined as 2.54 centimeters. So you're gonna use a ruler, tape measure, or measure your height. In the doctor's office, you'll often see your height be measured as inches and feet, not really centimeters. So that is just something that is different here in, I think, mostly in the US. I'm not sure if it's in other countries, but I know growing up here, we always had our height recorded in feet and inches. Okay, so you don't need to know about the micron per se, so we're not going to talk too much about that, but there's a figure of the micron. And it has in units of well, there's a picture of the micron, but we can go over what the micron, like what the unit is. So don't pay too much attention about the picture. That's not important. What micron is, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So a micron, the micron is just a common name for referring to micrometer. So 10 to the negative 6 kilometers, or right. So a micron, same as the micrometer. So 10 to the negative 6. So when we're measuring, so the reason we showed that picture, if you see the picture, it's a pressure bar. So it's referring to, I think, the distance between the two needles. That is the distance, or like the separation is like a micron. So that's how that's on the level of how small a micron is. But don't worry too much about that. That's just giving you kind of overview of how these lengths, how they differ. Okay, so don't pay too much attention to that. There's a micron, Okay, so we already talked about a cubic centimeter. Well, let's just go over to more relationships about that. So just as a review, 1 liter is defined as exactly 1,000 cubic centimeters. Or like this. Because we know that 1 milliliter is equivalent to this formula, or sorry, equation, 0.001 liters, which equals 1 centimeter cubed. And there's a depiction of a cube on this slide, and I kind of went over that earlier. So that's the background for the cubic centimeter. Okay, let me just double check my notes and see if I missed anything. Okay, I don't think I did. Okay. Okay. All right. Okay, so when we're talking about the metric units, so when we use metric units, right? When we're doing those exercises before, these metric units will be very helpful in doing dimensional analysis. So knowing the metric units and their conversions will help you, and we can go over some of them right here. So the metric relationships or metric units. Metric relationships. For example, so say I have 1,000 units per kilo unit. 1,000 units per kilo units. Kilo unit, sorry. So 1,000 units per 1 kilo unit, or 1 kilo unit per 1,000 unit. So we can say, if I start out with my base unit, I want to use this the second fraction on the right to convert to kilo units. So you see that my unit is getting smaller because I'm dividing by 1,000. And then if I start with the smaller unit, well, not the smaller unit, well, the unit that describes a bigger amount. So say kilo unit, if I start with something like my kilo unit, then I should be multiplying by 1,000 to get more of the smaller unit. So just remember where you start out and how much does the value make sense at the end. If I'm starting from kilo unit, I should end up with a number that's much larger than what I started with. Then if I'm going to reverse, I should end up with a number that is much smaller than what I started with, and vice versa. I feel like I said that twice, But if I start with the smaller unit, I should end up, so say I start with a smaller number, I should end up with a larger number. And then larger number, I should end up with a smaller number. Man, I feel like I'm saying that twice, or I just said that, repeat again. But anyway, just use these appropriate fraction for each time you're using the metric unit. So it's like the dimensional analysis and those equations we did in the exercises. It's a lot like that, but now we have more conversion factors. Okay, then 100 centi-units. So these are the most common ones. Units per unit. And we have 100 centi-units per U and 1 U per 100 centi-units. Then we'll go even smaller, 1,000 milliunits. Units per unit. So 1,000 milliunits per unit, and then 1 unit per 1,000 milliunits. So the unit can be whatever it is, volume, mass, or length. Okay. All right, now let's get back into some of the active exercises. So we'll use the last seven minutes to talk about these exercises. Okay. So here's another active exercise. So please try these before you actually listen to how I go over them. So active exercise. So say, how many grams are in 0.711 kilograms? So whenever it's less than 1, you can't say kilograms. So you have to say kilogram. Okay. So what we're given is 0.711 kilogram. So I'm just going to write them as the symbol, kilogram. So this is a metric mass units. So what we wanted is metric mass units, or the grams. So we know that 1 kilogram equals 1,000 grams. And our formula, we want to solve for grams, right? So grams is going to be on top over 1 kilogram, right? Because if we say this, like so, divide by 1 kilogram, both sides of the equation, and we get our equivalency factor right there. Okay, so like we did before, we just put these two together. 0.711 kilograms times 1,000 grams per kilogram. Our kilograms will cancel out like so, and then we get 711 grams. So we do a little mental check here. We started with 0.711 kilograms. And since we started out with the smaller amount of the larger unit, we should get a number that is larger than the smaller unit. So grams Grams in the metric system is lower than kilograms, so we should get a number that's much larger than what we started with, and we do in fact do that. So 711 grams. So you can always do a mental check to see if your answer is right. It's very common to get these metric unit equations. When students do these, they have a tendency to mix things up sometimes, so it's always good to do a little mental check. Okay, so everything's okay. Smaller value times larger unit. So we should get a larger value for the smaller unit. Okay. Hopefully that was okay. So let's end today by doing one more. So this is just great practice because on the quiz, you'll definitely see a type of this problem where you have to convert. So I encourage you to always practice these exercises to reinforce your learning. All right, so convert. So now we're going to convert 5.25 times 10 to the negative, 10 to the 5th milligrams to kilograms. So let's convert that. Okay, so, try these on your own, but now I'm going to talk about how to solve them. So what we're given is metric length units milligrams. And what's wanted is metric length units Wait, no, that's not correct. We don't want length. We want grams. Sorry. That's incorrect. And I will have to correct these slides. So we want metric mass units, right? Let's correct that. Sorry, guys, I don't want to confuse you, but I even got confused myself there. So kilograms. So we want kilograms, right? So 5.25 times 10 to the 5th milligrams. So we take milligrams there times 1. So we know 1,000 milligrams isn't 1 gram, right? Because we're going smaller unit. So when we go below the basic unit, that means more the smaller unit will equal to one of the basic unit, right? So for in this case, 1,000 milligrams is per 1 gram. Times. Now we have to do another conversion because now we need to go to grams to kilograms. So since kilograms is the larger unit, now it's going to take more of the basic unit to reach the larger unit. So in this case, 1,000 grams equals 1 kilogram. You can also combine these two fractions right here, but that might be hard to kind of, when starting out, it can be hard to memorize or memorize that. But if you want to condense your equations, as long as it's correct, you can do that. So in this case, 1 million milligrams is equal to 1 kilograms. So that is something you can also do as well if that's easier for some of you or some of the students. Okay, so then we get 0.525 kilograms. So when you're doing the metric units, in theory, you don't need to use a calculator. You could just use scientific notation and move the decimal point back and forth, and you should be able to arrive your answer in a pretty straightforward fashion. But don't worry, calculators will always be provided on quizzes if you need it. I understand, but you should be able to do, basic math operations like addition, subtraction, even with decimals. But I understand if you don't, people don't like decimals. I understand this is not a math class, but that's just my take on using calculators and how to use scientific notation. So let's check our larger value. We start off with a larger value of the smaller unit. And now we should get a smaller value for the larger unit. So I know these two terms may seem conflicting when you're talking about them in a sentence like that, but just make sure once you start out with a larger number for a smaller unit that the number that gets popped out at the end is larger. Is smaller for the larger unit. So kilograms is larger than milligrams. So if we start out with a very big number for milligrams, our number at the end should be small in comparison for kilograms. And in fact, that is what happens here. Okay. All right, guys, that is it for today. Sorry for rambling and seeming a little bit unorganized. I just want to make sure what I'm saying does not cause any confusion. And if I don't know anything on the spot, I will say I don't know, or I will take a few moments to kind of research and look up what I'm trying to say, just to back up what I'm teaching you, so no miscommunication or misinformation is spread. Because online there's always like many sources of information about chemistry, and some are correct and some are just plain wrong. So I don't want to feel like you need to go look up information just to double check my claims. So I always will take time to explain, and if I don't know something, I'll maybe pause and look it up so I could better communicate on these concepts, because chemistry can be tricky. All right, guys, that is it. Sorry about a little ramble at the end, but if any question, as always, email me. And I made an announcement about the OWL homework. They should have extended the grace period. I do not know why some people can't access it, even if they already have purchasing access. Or they purchase access. So if you still can't enter OWL, let me know. And for those of you who still can't enter, by tomorrow, I will probably have to send an extension. But right now, I don't think that's the case. But if you still don't have access, let me know. But anyway, guys, this has been lecture, I think, 4 now. If you have any feedback, let me know. But anyway, have a great rest of your day. Great great start to your week, and stay safe. All right, guys. See ya.